Vectors can also be used to plot functions, but by functions I mean mathematical functions, such as f of x equals an expression of x. For example, if we wanted to plot the sine function. So far, the only way we know is to hard-code each data point separately, but hard-coding each data point seems ridiculous. We'd start the same way as before, CLC and clear and close all. We'd define our x data points, so 0, pi over 2, pi, 3 pi over 2, and 2 pi, and we already know the values for y, which is sine of x, for each of those x coordinates. Then we could plot y versus x by doing plot x comma y. But not only is it ridiculous because there's a lot more data points to code, but it's also inaccurate. With 5 data points, MATLAB connects the dots using straight lines. So that doesn't look like the sine function. The first reflex is of course to add more data point. Let's add pi over 10, pi over 8, pi over 6, and pi over 4 with the equivalent sine y values. But if you look at it, it's still not the sine function. And you realize that that can't be possible. There's no way this is the only way to do a plot. We need a lot more data points. So MATLAB offers a function called Linspace, which generates a linearly spaced vector with n data points. N is optional, but defaults to 100 if omitted. So, in the example that we just did, by using 9 data points, we started seeing the sine function. Maybe if we used 40 linearly spaced data points, we could see a nice curve. Now what does linearly spaced mean? We could have 40 data points, but all squished at the beginning. That still wouldn't help us. So instead, we're going to linearly space them, so equally spaced with respect to each other, from 0 to 2 pi. Linspace does that automatically. So again, if I only use 5 data points, 0, pi over 2 pi, 3 pi over 2, and 2 pi, and I run, it doesn't look like the sine function. If I increase to adding 4 more points with their equivalent, sine pi over 10, pi over 8, pi over 6, pi over 4, it starts looking like the sine function. But there is no way we're going to keep doing this to figure out how smooth it needs to be. So that can't be the right way. So instead of actually coding the points one by one, I asked MATLAB, Linspace, to create a vector of equally spaced value from 0 to 2 pi, that's A and B, 0 to 2 pi, and let's do 40 data points. Maybe that will be enough. How do I actually calculate the y? Do I actually mentally calculate each data point to hardcode them, or do I tell MATLAB to do it? MATLAB has the capacity to calculate automatically. Since I was in radians at top, I'm going to stick to radian using sine and not sine d. This time when I run, the curve looks very smooth. Maybe I did too many data points. The interest of reducing the amount of data points is to save memory. If one day you're limited in the amount of memory you have, for example a space shuttle, then you might want to reduce it to exactly what you need. Maybe we could do 30. Notice how easy it is to change. 30 still looks smooth, maybe 20. At this point, if you look at the bottom here, it's definitely not smooth anymore. So 20 is too small, maybe 25. That seems accurate. Again, Linspace linearly spaces each data point. I didn't have to calculate exactly what the x-coordinate was here, or here, or here. MATLAB did it automatically. I asked for 25 points from 0 to 2 pi. That includes the extremities. So let's move on to vectors and math operations. We've seen that in MATLAB, vectors can store a single xy coordinate. They can represent physics quantities, such as magnitude and direction. We saw that with the robot example a while back. But they can also store a collection of data points to plot. This has nothing to do with physics anymore. X, Y, MATLAB can easily connect the dots. However, when we start doing calculations, other than sine or cosine of x, MATLAB follows the mathematical rules of adding, subtracting, multiplying, and dividing vectors. Adding and subtracting are okay. We've done it before. If we add two vectors, MATLAB adds all the first element first and the second component second. You can add or subtract a vector if they have the same dimension. Multiplying and dividing vector, however, can only be done under certain condition, and that's MA345. Since this is more for a freshman level, that's not exactly what we're trying to do. For example, if I wanted to plot x squared, if I follow the same process as the example before, it would make sense that I define my x's, and then I square it. I write the equation. But at that point, we've switched to vector operation. And MATLAB follows all the math books. That's not what we want to do. We want to multiply -10 by itself, -5 by itself, 0, 5, and 10 by themselves. Luckily, the arrow message gives you a hint. It says to use the element-wise power, and that's the dot caret instead. It won't be uncommon for you to use equations in freshman level. Polynomials such as these are easily used in equation of motions. When you want to define a trajectory or velocity, acceleration, you will always have a polynomial expression. So how can we tell MATLAB to ignore the vector operation, but instead follow more of an element by element operation? Look at the example again. Here I didn't do x squared. I did -5 times x squared minus 3. But the error is the same. MATLAB does not like squaring a vector. So here it is. I followed exactly the pattern of the sine example before. My x values are defined, my y value is an equation, just like sine of x, and then I did the plot, x comma y. But when I run, MATLAB crashes on line 12, which is the y expression. It tells us to use the dot caret instead. We want to do element per element operation. We don't want to do vector math. By simply adding that dot, MATLAB can plot the function. Now, same as before, it looks not really smooth. So in order to add more points, don't even try adding a single one. Go ahead and do Linspace immediately. We wanted to go from -10 to 10, but let's do 20 points instead. And run. Now it's curvy, and it looks like the curve of -5x squared minus 3. So remember, we really don't want to do vector operation at this time. We want to do element per element. Let's do a concrete example of graphical solutions. Suppose a car speeds in front of a cop at a constant speed of 20 meters per second. The speed limit is half of that. The cop starts chasing the car instantly with a constant acceleration of 3 meters per second squared. Using graphical analysis, at what time does the cop catch up with the car, and how much distance does it take to meet? Going through the steps. Two givens, the velocity of the car is a constant, and the acceleration of the cop is a constant. We are to find the time at which they meet and the distance at which they meet. As far as a little drawing, it's nice to actually realize that at the beginning the cop is at 0, the velocity of the car is constant, and we're trying to find the time and the distance when they meet. After a little bit of research in physics equations or physics books, the equations of motions are used. The position of the car at any given time is easily calculated by an expression, the initial position of the car plus the velocity of the car times the time. A similar equation can be written for the cop, but the cop is actually accelerating. So if you notice, we have a third term in the equation, which is half times the acceleration of the cop times t to the second. Now, in order to move on forward, we kind of need to assume and simplify the equation. The position of the car and the cop at the very beginning is 0. That's when the cop starts chasing it instantly. The velocity of the car initially is the velocity of the car. Remember that it is constant, so that's 20 meters per second. The velocity of the cop initially, well, he wasn't driving. Then he instantly started driving. So we can assume that it's 0 meters per second. This simplifies greatly our equation. The position of the car at any given time is 20 times t, and the position of the cop car at any given time is 1.5 times t squared. So hopefully if we can plot these two together, we might be able to find an intersection when the distance is identical. Step 5 and 6 are not required. We are to solve graphically. But 7a can still be done. Since we're going to code, let's start to do an outline of our problem. Let's not jump ahead of ourselves without even figuring out what we have to do. We're looking for a time, so let's try to imagine that it's between 0 seconds and 60 seconds. The other reason to define a time is since our equations are always based on time, we're going to need it to plug it in. Once we've defined our interval of time, we're going to calculate the distance for both cars and plot them on the same graph. So starting from scratch, cop chases car by Caroline. CLC clear, close all. The usual basic command before we do anything. And then we've already developed our algorithm, so might as well copy paste it and work from there. To quickly make something a comment, just select it and add the comment. And then now we're on step 7b, where it's fill in the blank and code. So define an interval of time. Again, we're plotting a function. Chances are we want a lot of data points. So we're going to go from Linspace immediately from 0 to 60. Let's do 30 points. Let's calculate the distance for the car. That was 20 times the times. Let's go ahead and plot this one. Let's skip a step and see if that actually works. In the x-axis, I want the times. In the y-axis, I want the distance traveled by the car. Car, cop. It is normal that it is a straight line. After all, it is constant velocity. Let's add a title. Always add a title after the plot command. MATLAB needs a figure open in order to put a title first. So title always comes second. Distance traveled versus time. It's also nice to add a label to the x-axis. Similarly, we have a command called xLabel. So in the x direction, we have the time in seconds. Y-label is a distance, and that was in meters. It still works. Notice how I'm testing as I go. If something doesn't work, I'd like to know immediately. Instead of trying to debug and fix errors on multiple lines, I know immediately where I have to go. So, the car works. Let's do the cop. This distance traveled by the cop was 1.5 times times squared. Again, run immediately. Since this is the only line that I typed, I know the error is right there. By reading the error, compute element-wise power, use the dot caret instead. Remember, We're trying to do element per element operations. We're not doing vector operations. So, alright. It still works, but I have to plot it. Now here's a challenge we haven't seen before. How do I combine two plots on the same figure? It's actually already built into MATLAB. The plot command can accept an x and a y coordinate multiple times. So if I want to plot a second set, I just have to generate times and distance by the cop. So at least we have two plots. Now, 60 seconds might have been too big. Let's reduce it to 20 seconds since the intersection is obviously around there. The second argument changes to 20 very easily. Let's add a grid so we can easily read the intersection. Alright, now which one is which? Which one is the cop, which one is the car? Remember that when you do plots in engineering, you need to label absolutely everything. So the additional one that we need is a legend. Is the green the car or the cop? Well, let's do a legend. Notice how MATLAB is very intuitive as far as the keywords. The first plot that we did was the distance for the car, so that's the first one that we need to put. The second one was the cop. So now we could print this. Although if we're printing in black and white, we still have something to do. Let's try to put markers on each. Now where do the markers go? They used to be the third argument. They remain the third argument. In between the two plots, I need to do maybe diamond, straight line. And for the cop, I'll do a little plus sign with dash dot. So now I can print in black and white. But we still haven't answered our question. When does the cop reach the car and at what distance? So by zooming in, you have the zoom in command here, we can easily figure it out. Well, it looks like the cop caught up at 13.4 seconds, and that was about 260 meters. So that answers our problem. Graphically, we didn't have to solve any equations. Again, plotting can do two plots at the same time or multiple. We could continue that way. But always repeat the X, Y line specification. X, Y line specification. As far as the equations, they were rather simple. Though we did have to use the dot caret in order to do our operation element per element wise. To conclude, the whole purpose of this tutorial was to plot functions. And when you do that, you never really want to hard code one element at a time. Always ask MATLAB to create a huge amount of data points. Linspace is generally used. Vector multiplication, however, requires knowledge of higher math. This is a freshman class, so we can't possibly ask to do vector multiplication. Fortunately, MATLAB also knows how to do element per element operations. Use the element per element operators. And the plot command can of course be used to plot multiple plots. Remember that if you're plotting in black and white, add the markers. The important keywords here that are very intuitive is the title, the X label, Y label, and the legend. And that's it. Now you know how to plot multiple graphs on the same figure and answer questions graphically.